in this chapter talk about vectors, which when you take physics, you'll cover that. So we don't do it here. They talk about dot products, and then they also talk about complex numbers in trig, and we decided that's not the most important thing for us to cover. So imaginary numbers are imaginary to begin with, and then we can also put them in terms of trig as well. But we do not talk about those. So we end our trig with these two different laws, law of sine, law of cosine. So we're going to do a little intro. I'm going to show you how the sines was created, and then we'll talk about how to use that. This week we're going to go over the law of sine the rest of the week, and then next week, Monday and Tuesday, we'll go over the law of cosine. Right now, I have a test on this, ready for Thursday next week, and then we'll be done with trig.
Chill.
Not tomorrow, Thursday. Next Thursday. So next Thursday, it looks like we should wrap up this, have a test, and then we will be done with the trig portion of the class.
I remember this.
So just a little refresher about notation and the types of triangles we have solved. So we have looked at the right triangle. And when you label a right triangle, it has three angles, and we usually call those angles. How would you label the angles? What letters do we usually use? A, B, C, because Pythagorean theorem is A squared plus B squared plus C squared
Equals C squared.
equals C squared.
Not plus.
C, yes, thank you. C is generally the right angle. And then when you label the sides of a triangle, you label the letter to match with the angle. So whatever side is across from the angle should be the corresponding letter. So if it's an uppercase C for the angle, it would be a lowercase c for its corresponding side. And it's always the one that's directly across from it. So side B across from B, side A across from A. Lowercase always denotes a side. Uppercase always recognizes or represents a angle. You'll never see in trig the little angle mark, or very rarely will you see the little angle mark that you would have used in geometry. It's just, if it is an uppercase A, it's always an angle. So it's implied uppercase are angles, lowercase are sides. So we're going to cover oblique triangles. So there's right triangles and there's non-right triangles, which are called oblique triangles. These triangles have no right angles. And there are two types of oblique triangles. The first one is an acute triangle. What's an acute triangle? Anna? Scalene, what's that mean? Two of the sides are angles are smaller than the third. What else does it mean? Oh, the sides are different. What has to happen with an acute triangle? Carrie? All the angles have to be less than 90 degrees. So an acute triangle, every angle is less than 90 degrees. That makes it acute. We would still label the angles A, B, and C, but they can pretty much go anywhere. Sometimes you say A is the smaller one, C is the larger one. Might not always be the case. But the key thing is, again, labeling the side corresponding with its angle. So acute means less than 90 degrees. All angles are less than 90 degrees. That's what makes an acute triangle. So if it's an obtuse triangle, that must mean then, Carrie, if it's obtuse, yeah, one angle is larger than 90 degrees. Now, only one, because that takes away from your total of 180. So the other two can't be larger than 90 degrees. Obtuse angles generally have that wide opening. The angle is wider. So I'm just going to label that with the C. And then the A and the B can be either location. So obtuse has one angle that is greater than 90 degrees. So underneath the two diagrams, there's one little summary that we're going to just kind of talk about today. And then we are going to see how the law of sines works. That's what we're going to focus on this week. So underneath it kind of tells you a little bit about solving oblique triangles. Any triangle that isn't a right triangle. To find the remaining parts of an oblique triangle. So again, when you're solving for a triangle, you're trying to find all the pieces. Generally, we try and put it in a word problem format, but we really are trying to find the missing sides, whatever sides are missing, whatever angles are missing. Going back to geometry, you learned congruency statements for triangles. It says here we have ASA and AAS, and that is when you have two angles and a side. Does anybody remember what ASA stands for? Angle, side, angle. So making a little diagram, why would you use these, like why in geometry or how in geometry did you use them? Anybody remember what you used them for in geometry? Carrie? To prove that triangles are congruent. So you use these two pieces of information to prove triangles were congruent. Whether you had angle, side, angle, and if you had both of those in two triangles, then the triangles were congruent. So you used to show that they were congruent. In trig, we're not showing triangles are congruent. Instead, we're using them to help us find parts of triangles. So as a little reminder, if you have an angle, a side, and then another angle, the side should be squished in between it. That's what angle, side, angle is. So you have an angle, you have a side in between, and then you have another angle. Those angles are going to be different. That's why I have two little tick marks here. If you have angle, angle, side, you're going to have an angle. You're going to have another angle, and then the side has to be across from one of those two angles. So wherever that side might be, it's going to be across from them. If we have that information, so if we have angle, side, angle, or angle, angle, side, we're going to be using the law of sines to solve for it. So based off of the information we're given, that information then would be applied to the law of sines. So if I have those two types of triangles. The third one says two sides and an angle opposite of one of those, and that's side, side, angle. So two sides and an angle opposite of one of them might be a situation like this. Now, I don't know who you have for geometry because you could have had it here with Mr. Warnock or Mr. Cummings, or you could have had it next door with any of the three over there. Does anybody remember what happened with side, side, angle? What did they tell you about side, side, angle? Emma? It's not a thing. It is a thing. You can't use it to prove triangles are congruent. Because there's actually a couple of cases going on with side, side, angle. And in geometry, they do tell you that no, you can't use it to prove things are congruent. However, in trig, we say, well, actually, you can if certain conditions are met. And we're going to do an activity tomorrow with a protractor and some exploring to see what happens with this special case. So this is a special case. And we're going to investigate that special case tomorrow. So it's a totally separate case, but it actually is a thing. But we still say side, side, angle, not angle, side, side.
Why?
No swearing in church. The other options that you also learned about last year, or not last year in geometry, would be if you had three sides. So if I have three sides, you also can't use that to prove triangles are congruent because, if the three sides are different, then they're not going to be congruent. And then you have the side, angle, side, which are two sides and then the angle squished in between them, wherever that happens to be. If I had those two options, then I'm going to be using the law of cosines, which we'll talk about next week. So the key thing is here with these two laws is that it depends on the information that you're given, which one you would choose to use. So based off the way the information is given, the way the triangle looks, we would have to use sine versus cosine. So we are going to talk about sine today and why it works, how it was created. We're going to do a tiny little proof. So if you flip the page, there are two cute little diagrams drawn. So our goal is to find angles and sides to be able to solve for any part of a triangle. So the information above here says for a triangle with sides A, B, and C and opposite angles, I'm just going to change these to A, B, C as well. Just change them to A, B, C so they match. But it is trig, so trig uses all of the Greek letters in a true definition. So we have two triangles that are drawn. The first one is the acute situation that we drew on the previous page. And angle A is right here on the left. So that's angle A. And then we have the obtuse situation, which is on the right side. And we're making angle A also that obtuse angle. So you have two diagrams drawn. But notice in those two diagrams, we have a, does anybody remember what that line is called that you drop down? What is the name of that? When you drop a perpendicular line down in a triangle. Perpendicular line. It is the height. It begins with an A. Yeah, it's the altitude. So that's our altitude. Yeah, you were going to say that. So we're making a right triangle inside of it because really everything's based off of a right triangle. We're going to try and prove this law of sines or show you how it was created. So if you're talking about the law of sines, you're probably going to use what function in the equation? Sine. As if it's the law of sines, it probably uses the function sine. Right? Make sense? So if I told you to tell me what the sine of angle A is, and I'm just picking that one on the left, what would the sine of angle A be based off of, let's use the acute triangle, it's a little easier to look at. What would the sine of angle A be in the acute triangle? Josh?
H over B?
H over B. Because we have this altitude that is dropped down for us, it does make a right triangle. And if you're using the sine, it has to be a right triangle when we use those proportions. So the height over the hypotenuse. Sine of angle A would be the height over the hypotenuse. We can also find the sine of angle B because it's on that other corner right here. Josh, the sine of angle B would be H over A. B is on the other side. It's also across from that perpendicular altitude, which forms our 90-degree triangle. So we have a triangle on the right or left and a triangle on the right. What do you notice that's similar in both of these? The H, and they both have an H in the same spot. Same location, it's in the numerator of the fraction. Brenton, if I asked you to solve for H, how would you solve for H? Yeah, in this one we multiply the other side by B. So we would have B times the sine of A. Which you actually did way back in geometry when you started figuring out the height or the altitude of the triangle. On the other side, I can do the same thing, except I multiply by A, and then the height would be equal to A times the sine of B. So again, we're trying to create this law of sines so that we can have something then to use. So we're working on creating it. It says proof, which, yeah, we're kind of proving it, but we're really just kind of working through and creating it. So Brenton, if you have two equations that are equal to the same variable, what can you do? You can set them equal to each other. So we're going to take them and set them equal to each other. So we have B sine A is equal to A sine B. So now we took the height out of the problem because I said we wanted to solve for triangles that weren't right triangles, and we don't want to force it to be a right triangle. So by taking the height out of the original equation, we no longer have to have the height in the problem. So taking this little equation here, B sine A equals A sine B, I'm just going to tweak it a little bit so that I can pull the variables together that are the same. So we have a b and a sine b on the other side. How could you pull those two angle side, kind of pair them together? What could we do to get them on the same side of the equation? So how could I take the sine b and take it over so that it's with side b? Not a trick question, Brenton. Divide it, yeah. So we're going to divide by sine b. We're just trying to pull the angle and its corresponding side together. We're going to do the same thing. We're also going to divide by the sine of a. So doing that gives us b over the sine of b. That's equal to a over the sine of a. And that is the law of sines. So it's a proportion that enables us to solve for parts of the triangle if you have two sides and an angle, or if I have two angles and a side. So the law of sines actually goes one step further and says if you set a proportion, a ratio equal to another ratio is a proportion, a over the sine a can equal b over the sine of b, can also equal c over the sine of c. Because remember, we no longer have right angles. So any of those two ratios paired together makes a proportion, and a proportion creates an equation that we can solve for. So as long as we have two sides and an angle, or two angles and a side, we're able to solve for the other parts of the triangle. So the law of sines was created from a triangle being made into two right angles. Everything still goes off of what you know. That's how new things are created. Taking the old, using the old, creating the new. We don't always have to have a right triangle. We could force everything to be a right triangle, but there has to be another way around it. And there is, because now we have the law of sines. So this one works pretty easy. It's pretty much a formula. We're going to plug numbers in and see if we can work through it. So on the back, I believe it's the back of that page, there are two problems. One is just a standard problem that is not a word problem for you to see how this works, how we can solve for the other parts of the triangle. And then, of course, we have a word problem because most of trig really are applications. At the bottom of your page, I kept it at the top of mine. We're going to be using calculators because very rarely will we have values that are exact. Anytime you have to plug in the sine of a random angle, it's not going to be exact unless it's still that 30, 60, 90, the ones we have memorized. So we will have angles that are not specific angles that we have memorized on the unit circle. So you will need a calculator. When using the calculator with the law of sines or the law of cosines, it says hold all immediate calculations in the calculator without rounding. So all that means is you're not going to take the sine of 102.3 degrees and round it to be whatever that number is, and then take the sine of the other angle and round it to a number, and then use those two rounded numbers in your formula to get another rounded number. So the goal would be to keep everything in the calculator, use the second answer function so that nothing is rounded until you get to the final answer. It keeps angles and sides more exact. The less rounding, the more exact. So we have a triangle. That little guy here, this is a lambda. We'll just make it a C. So we have angle C being 102.3 degrees. Angle B is 28.7, and then side B is 27.4 feet. It says find the remaining sides and angles, and then it says that this is an angle-angle side case. So we're going to draw a little diagram. This angle is obtuse, so your diagram should kind of mimic the information that you're given. If you have an obtuse triangle or an angle that you're given, then we can make the diagram match that angle. And that is angle C at 102.3 degrees. I'm going to label side C right across it. The other two, it doesn't matter where you place them. So totally up to you. We have angle B. You can place it at the top. You can place it at the bottom. It's 28.7. As long as side B is across from it, that's the part that truly matters. And then we have angle A. And the other information they give us is side B, and it's 27.4 feet. So if you look, it says angle, angle, side, and this is an angle, angle, side case. I have two angles with the side not squished in between the two angles. When you have this information, we can use the law of sines to help us solve. But before we solve, is there anything else we can find without using a fancy new law of sines? Emma? Yeah. So we should be able to get angle A by taking 180 degrees minus the two angles that you're given. So she said add those two up, subtract them from 180, and that should give us that angle A. And that's just knowing you have a triangle. All triangles have 180 degrees inside. So Emma, what would the value for angle A be? 49. Don't forget the little degree mark. So we're back in degrees. Radians are gone.
No.
I know, right? So now we're going to try and use the law of sines to help us solve for the other missing parts. And now we have three angles, so we have two missing parts. Does anybody know how we could set up the law of sines? So thinking about that it has to be a fraction, one fraction ratio of a side and an angle equal to another fraction or ratio of a side and an angle. So kind of look, what side and angle go together? How could we create that as a fraction? That's what we're doing with the law of sine.
Can we set up a proportion with A over sine A equals B over sine B?
Yeah, so let me label this here. So she said if we take side A and angle A, so we don't know what side A is, but I could keep it as A. We have angle A, which is 49 degrees. So the law of sines says take the side over the sine of its matching angle. You set that equal to another side. Well, we have B, 27.4. And we're going to take the sine of its matching angle, which is 28.7 degrees. That's how you set up a proportion. One ratio, side to angle, equals another ratio, side to angle. And now we solve. So how are you solving for A? How do you get A by itself? Hannah? So we can multiply by sine of 49. What else could we do? Cross multiply. When you have proportions, the easiest thing to do is cross multiply. What Hannah said was not wrong. It just might take us a couple extra steps. But if we cross multiply, that takes a proportion and it takes it out of fraction form. So we have A times the sine of 28.7 degrees. That's going to be equal to, I'm placing the number first, the side first. So 27.4 times the sine of 49 degrees. So that's like having a coefficient in front. And then to get A by itself, we would divide, and you get 27.4 sine of 49 degrees divided by the sine of 28.7. So in your calculator, do not round any little piece. So you're going to plug in 27.4 sine 49. Make sure your calculator's back in degrees. You're dividing that by the sine of 28.7. Carrie, what'd you get? So that would be side A. 43.1. Did anybody not get that? Make sure your calculator's in degrees, not radians. So that is side A. If we go up here, 43.1. And then we need to do the same thing to find side C. So go back to the original proportion. You can keep this using the information for B, but now on the other side we need to find C. So setting up C over the sine of 102.3. I'm still going to use B. That was the information that was kind of given to us, so we might as well use that information in our problem. If you use an answer that you found that you rounded, then again we consider it less exact. So we try and use the given information in that ratio twice, or in the proportion twice. So when you plug C into your calculator, you should have 27.4 times the sine of 102.3, and then you're dividing that by the sine of 28.7 degrees. I need to see the original step, the ratio, proportion, and then I do need to see what you plugged into the calculator. Because it's attached to the biggest angle, it should also be the biggest side. If it isn't, then you did something wrong. But the size of the angle should be proportional to the side. Biggest angle, biggest side. Smallest angle, smallest side. So, Carrie, what'd you get here? I get a little more. 55.7? Is it 7 or 6? 7. There we go. But just looking at all three sides, you can see that the smallest angle does have the smallest side, the middle angle has the middle side, the largest one has the largest length. Questions? So if we had this problem in chapter 4, we would have made it a right triangle, and then we would have solved for all the extra parts in order to eventually go and find this. It would have been a little more longer of a problem. Questions? So that would be the just generic type of problem, and I think like 9 and 11 and 15 are your generic problems. So just giving you a diagram, or you're drawing a diagram with a couple of sides. So that would be like the generic, no word problem involved. The other type of problem, of course, lots of applications in trig. So we have the Coast Guard, and there's 2 stations for the Coast Guard. We have Station Zulu, which is located 120 miles west of Station X-Ray. A ship at sea sends an SOS call that's received by both stations. The call to Station Zulu indicates that the location of the ship is 40 degrees east of north, and the call to Station X-Ray indicates the location of the ship is 30 degrees west of north. How far is each station from the ship? And then I think part B says if the helicopter is capable of flying 200 miles an hour, how long will it take to get to the nearest one? So, lots of information. We're going to try and draw a diagram. Which would go on the left and which one would go on the right? So we have these 2 stations. Read back through the first sentence there. Reese, what do you think? Yeah, Zulu's on the left because it is west of X-ray. So if it's west, it has to be on the left side. So right here. And that distance in between is 120 miles. The next piece of information talks about some bearings. So starting with Zulu, it says the location of the ship is 40 degrees east of north. Drawing in my little coordinate here so that we can get an angle. It says east of north. So we have the northern direction, and we're moving east of it. 40 degrees. Doesn't say how far, because that's what we're going to try and find. Our goal is to find the distance from that station to the ship. And then the other one, X-ray, says the ship is 30 degrees west of north. So here's north, we're moving west by 30 degrees. So our ship is somewhere here at sea. You had a problem very similar to this on the chapter for the last test. But it was like on the review. And when we solved it, we ended up making triangles on the outside because we had to make it a right triangle. We did a whole bunch of finding pieces and then adding those pieces, subtracting the pieces. It was a really long problem. We don't have to do that way anymore because now we can just plug stuff into a short formula. So Brenton, if we know the two angles on the outside, the angles on the inside would be
50
and then 60. Our goal is to find the distances on the other sides. You can label them however you want to label them. So if this is X-ray, you could say across from it is X. If this is Zulu, across from it is Z. Or if you want to keep them as A and B, keep them as A and B. Totally up to you. Brenton, if the two angles are 50 and 60, the leftover one at the top would be 70. And we need that angle so that we can then set up the proportion. So Lauren, can you solve for one of the sides? How do we do that? Give me a little ratio here. So 120 was the information that was given, as well as 70 degrees. And then, doesn't matter which one you want to solve for first. So Z over the sine of 50. So we're really taking 120 times the sine of 50, dividing that by the sine of 70 degrees. And then you're going to do that a second time because we also need to find the other distance. So going back to that original information, the given values were not rounding. Anybody have Z or X? And Emma, what do you have?
Z is 97.8.
Is this in feet or miles? Miles. So Z is 97.8. That distance is actually from X-ray to the ship. So if you go back and look at your diagram, even though it says Z, that doesn't correspond with the distance from Z. That actually corresponds with X-ray's distance. So X-ray is 97.8 miles from the ship. How far is the other location? Carrie, do you have the other location?
110.6 miles.
And that would be from Zulu. Questions on finding that distance? how far is each station from the ship? We've now stated how far the distances from each station would be. Just make sure that you're pulling the correct pieces of information. The second part, if a helicopter is capable of flying 200 miles an hour, it's dispatched from the nearest station to the ship. How long will it take it to reach the ship? Well, the nearest station is going to be X-ray. And that was 97.8 miles. How do we figure out how fast it would take this helicopter to fly to the ship? So we know the distance. We know how fast the helicopter's flying. We want to know how much time it takes. How do we do that? Yeah? Speed over distance? So she's saying speed over distance. Does anybody remember what the little formula is if you have a distance, a speed, a time? Distance is equal to rate times time. So we're actually going to flip the little proportion that she gave me. Because if I want to find time, I need to take the distance value and divide it by the speed. Or the rate. We also call that the rate. So your distance, the total amount of space you're traveling, and then dividing by how fast you travel. So tonight's homework, the first 1 through 6. Those problems are just kind of informational problems. You're not really solving any problems. And then the other group of problems, the last 6 are the ones